equilibrium situation on horizontal surface. Dylan is pulling a toy car of mass 5 kilograms on a rough surface. The string makes an angle of 53,13 degrees with the horizontal. If he applies a force of magnitude 25 newtons and the frictional force is 15 newtons, determine the acceleration of the toy car. Also, determine the normal force exerted by the pavement on the car. Solution. Before we proceed, let us identify the situation. The surface is horizontal. It is rough since the frictional force is given. We assume that the body is in non-equilibrium state. Let us find the forces acting on the car and draw its free body diagram. The force of gravity, Fg, is acting in the downward direction. The normal force acts perpendicular to the contact surface, that is the pavement. Note that the normal force has been drawn at the center of the car to keep the diagram less cluttered. In reality, there are normal forces at the front and rear tires that are collinear vectors and can be added. There is a force applied on the car by Dylan. There is also a frictional force opposing the motion of the car. That completes our free body diagram. The applied force, F applied, can be resolved in two components, the one acting perpendicular to the pavement and the other acting parallel to the pavement. The plane of motion is along the horizontal surface, so the net force in a direction perpendicular to it is 0. Vector F R y equals vector n plus vector F applied y plus vector Fg equals 0. Taking the upward direction as positive, we get vector F R y equals n plus F applied sine theta minus Fg equals 0. N equals Fg minus F applied sine theta equals mg minus F applied sine theta equals 5 times 9,8 minus 25 sine 53,13 degrees equals 29 newtons. Therefore, the normal force has a magnitude of 29 newtons in the upward direction. We can apply Newton's second law to the motion of the car along the pavement. Vector Frx equals m vector Ax. Vector Frx is the vector sum of the forces parallel to the pavement. Therefore, vector Frx equals vector F applied x plus vector F. Taking the leftward direction as positive, we get vector Frx equals F applied cos theta minus F. Combining 1 and 2, we get m vector Ax equals F applied cos theta minus F equals 25 cos 53,13 minus 15 equals 0 Newton. The acceleration has come out to be 0. Therefore, the toy car is in uniform motion and no net force is exerted on it.
Starting to feel it? Now go master it with Maski.